All right, so that's 8:10. Let's get it started. Good morning again, and welcome to mechatronics courses. The first one that you're taking that actually is designed for mechatronics. This is MET 3100, and as you noticed in the name of the course, something changes this term. Now we are getting specific courses designed for mechatronics. And that's to say that things get a lot more interesting now, because it turns out that all of us chose the best engineering discipline to study, and that's mechatronics. Just don't tell the mechanical engineering students and the electrical. Now we get to study what you chose, which is mechatronics. So we are now amongst a group of mechatronics people, and we can start to do the fun stuff. So what you're going to do in this course is to develop more on the mechatronics side and use past courses that you took before. For example, control systems, dynamics, and electrical circuits. And you're going to put all of them together and try to come up with some comprehensive mechatronic systems. You're also taking this term sensors and instrumentation with Dr. Siu, I suspect, and that goes along the same lines. Is one very important part of a mechatronic system, which basically has, I would say, four main parts: the actuation system, the power electronic system, which is what you're going to cover here, the sensors and instrumentation, so that's Dr. Siu's class, and control systems, which you just survived. And this time, because we have a small class, we have less than 80 students, we are going to do our meetings online live, so we can interact more. And this will be very important in this course, is that we keep a conversation going around your design projects and around the questions that you have. So you just do control systems, and my impression of asynchronous lectures is that it's not the best way to keep people engaged. I could track views on YouTube, and I noticed that most of the views happen 3 days before the test. And so can't blame anybody, because it's very hard to just leave, to keep up with the content when you can just leave it for later. I would probably do the same. But it's something that we cannot do in this class. There is a lot of contents to cover. The contents will build on each other. And especially when it comes to your design projects, we need to talk during the semester at least every 2-3 weeks. So it's very important that you engage with your group members and with me during the semester, not only at the end of the semester, so that there are no surprises when it comes to the deliverables in this course and the expectations. Right. So again, now we are amongst mechatronics students. That's what we chose to do. So we might as well engage and do something meaningful at the end of this course. This is a very useful course. We'll see later for any mechatronics project that you're going to develop. You use the concepts that we are going to cover here. Some of you have probably already started to use power electronics without maybe not paying too much attention about the details when it comes to Arduino controllers and other sort of applications. So here we're going to go more in depth and see how they actually work and how we can interface electrical motors with microcontrollers and create some interesting systems. So today we are not going to have a lecture. We are going to talk about the course structure only. And so that's why we will just stay on a PowerPoint presentation. But I'm still trying to integrate the light board on the live lectures, but that's a bit trickier than recording lectures. So we'll see how that goes. So let's get it started with that. So you can see my screen now. Yeah, good. All right. All right, so let's go through the presentation. So these slides are posted on Canvas. I recommend you download them before our lectures, and then during the lecture, we can fill them out together and go through the details together. And also, this conversation here is recorded, and I will post it later. So you can always watch this later if you have some questions, but it is important that you come to class, even though it's 8 in the morning, and ask questions and interact during the lecture. So if we do any bonus questions, that will be done during the live lectures. Okay. All right, so I'm asking you that this time, this material that is provided to you should remain within us. That do not share this in outside sources such as Chegg, of course, Hero. You're not doing doing any good to the students that are coming after you. The idea is to use the resources you have at school and not inside them to look for information elsewhere when you have an entire infrastructure that is there for you to use. So please do not share this contents anywhere else other than for the purpose of this classroom. This class. So this is my email address. You've all taken control systems with me, so I don't think there's anything new here. So this is my email address. If you have any questions, you can email me directly using that email. It's better to do it that way than through Canvas because I have an immediate notification and then I can answer quickly. So for any questions, any inquiries, you can always email me there. Don't hesitate to ask whatever questions you may have. For my office hours, they will run this time on Tuesdays from 9:30 to 11:30. So just right after this meeting, I checked your schedule. This should work for, I would say 95, 99% of you. But if for some reason this doesn't work, we can always schedule additional appointments. Just send me an email and we can always meet outside of these hours. There's no problem with that, right? So we are going to be meeting at least every 3 weeks. And that's very important because you need to go over your design projects that we're going to talk about later in detail. So we'll have to meet outside of office hours anyways, right? So come to office hours, ask questions. The best way to ask questions is to, as you revise the lecture notes and you come across something that is unclear, just to write it down and come into office hours with a list of questions, and then you can address them one by one. Regardless of how many questions you have. And again, don't be afraid to ask questions. I'm not here to judge, I'm here to help. So for anything that is not clear, don't hesitate to ask, okay? So here we have the lab instructor and the TA. So you probably have had courses with Masood before. So he'll be running the labs for this course, and Ben will be running you'll be the teaching assistant. Some of you had him in control systems as well. And he's here also to help you with your design projects and with course content. So there will be no tutorials for this class. That's decided at the faculty level. So there are no tutorials, but we have a teaching assistant that can help you with questions, technical questions, or in particular with your design project, should you have any questions there, and we'll probably have some. So here we have their office hours. The link to their office hours is already posted on Canvas as well. Just go to the module where we have all the URLs, and you'll find their contact information there. Okay. All right, so our lectures are going to be on Tuesday and Thursday from 8 to 9:30. This is a good start for the day. And will be online synchronous. So the format this time will be, again, live, and I'm recording the lectures and posting them later. So if we get into a question period and you don't feel comfortable with your questions being or discussion being recorded, I can just edit that out later. Right? So don't be afraid of asking questions because it's going to be on record. I will crop that out from what I post later. And these will not be available, visible to everyone on YouTube, like the control systems lectures. Will be private, and only people with the link will be able to watch them. So don't be afraid of asking questions because of that. Labs will run bi-weekly as usual from Friday from 3:30 to 5:30, and they will be synchronous. So this year and this term specifically, labs will be a bit different. So you will not be required to go to campus at all. Everything will be run remotely. The difference is that you'll be given a kit that we purchased, and with that kit, you should be able to do the labs at home. Of course, we have to adapt some of the activities. So this is not the same labs that the students got last year, but well, we have to work with the conditions that we have. But it's still very useful, and I hope that you will enjoy them. So Masood will contact you soon to give you more information on how to pick up the kits from the school. At least one person from each group will have to do that. Right? But then once that's done, you don't need to go to campus at all. So you will be required to form groups as per the announcement that I sent on Sunday, groups of 4. And then once you have those groups, you can inform Masood or use the People tab on Canvas to do that. Okay. Any questions so far regarding lectures, the structure, or the labs? No? All right. Okay, so this is the recommended textbook that we're going to use. Is Principles of Electric Machines and Power Electronics. This is a very good book that I have based some of the lectures from. So if you open the book and you look at the cover page, you will notice that the author is wearing sunglasses indoors. So we have to be careful with how much we trust him. But it's a good book overall. The lecture notes will be available on Canvas. You can download them and use them in class. Right? So I had a question here. Does only one person get the required materials for the lab? Yes, only one person, but then you can do one lab each and give the materials to another person. So for each lab, one person can work on a specific subtask of the lab, and it can rotate. I understand that is not ideal, but unfortunately, that's the current situation, and that's what we can do at this time. Labs will start next week, yes, and Masood will be in touch with more information. Okay. The lecture notes. The lecture notes, yes, if somebody's out of the country, I think that will probably be a little problematic, as it would have been otherwise, if you had in class, in-person labs. Are the kits returned at the end? Yes, they will be returned at the end. If you can't get the kits from other members, then you can't. Then you can, one person will do most of it, and then other people can work on simulations, for example, that emulates the same system. Right? So all these small details, Masood can, if you're out of the country, well, no, not necessarily. That will not be a problem, but we'll probably not be able to deliver the kit to you. But you can work with others on simulations and reports and other things. All right, so the lecture notes will be available on Canvas. You can download them. And use them in class. Also, take the time to review the student conduct policy that is posted on the academic calendar. We are going to be very strict when it comes to that. Any form of misconduct or lack of professional behavior will not be tolerated at all. Right? We are now third year. Well, next year we'll be graduating. At this point, we expect a very high level of professionalism, which is exactly what one would expect from professional engineers. Any form of misconduct or any incidents of cheating will definitely not be tolerated, and that will go to academic misconduct straight. Right? Now, we are working on the subject that we chose. There is absolutely no excuse for cheating or other academic misconduct behavior at this point. Right, but that typically doesn't pose a problem with mechatronics. For the design project, do we have to provide a physical project? No, we'll go through that in more details in a little bit. Okay, so here is the structure of the course. We have 21 lectures, 5 labs, 1 midterm only, 1 final examination, and 1 lab exam. The lab exam will be included in the final examination. We'll just get questions that are specific from the labs, and they'll be included in the final exam. 1 design project and 4 assignments. The assignments will not be marked, but they are very useful. You can ask people who took this course last year, and they will confirm that the assignments are hard, and they are hard for a good reason, and they can help you significantly during the midterm and the final. Now, our objective here is not to simply regurgitate information to see how one example is done and then replicate that example. That's not how engineering works. Our idea here is to train our analytical skills and our problem-solving analysis, and analyze a problem critically and being able to provide the solutions to a problem that we've never seen before. That's how engineering works, and that's what I want the students to develop, is their sense of a critical analysis rather than regurgitating information. And that's maybe sometimes what makes my classes a bit challenging sometimes, right? But it's nothing out of the, it's nothing that extremely hard. For the grading policy, the final exam will be 40%, the midterm examination will be 20%, lab reports 20%, and then the design project, including the report and presentation, will be 20% combined. So 5 for the presentation and 15% for the design project report. And we're going to do some quizzes that will run live. The only requirement for the quizzes is that you attend lectures. So there will be no exception if you missed a lecture and you missed a quiz. That's what it is. Right? So these quizzes will only be available during the class. We're going to be using Kahoot for that instead of Canvas. Canvas is a bit boring for quizzes. And these are participation marks. These are bonuses that will be added to your midterm marks or final exam marks. Right? Up to 5%. I always say up to 5%, but I end up doing more. Anyways, it's a good idea to attend the lectures. So let's go over the grading policy. We have 1 midterm, 20%. The midterm will be on Monday, not Tuesday, so take note of that. Monday, February 22nd. So the reason I had to move this to Monday is to free 1 day so we can use that day to do the project presentations, as we'll see later. So that will be on Monday, February 22nd from 8:15 to 10:45. So that will extend a little bit. I checked with academic advising, and this should work for you based on your schedule. We have a final examination on the final examination period. That will be 40% of your grade, and it's comprehensive. It's all lectures combined. Right? And as I said, the final examination will include questions from the labs. Very simple questions just to check that all the work was not assigned to the same person all the time in a given group. The design project, we're going to go with more details over them later. They will be due on March 31st. So please note that March 31st is the deadline for the design project. So you are aware of this deadline today, right? And this deadline will not change, and there will be no exceptions. So there are no excuses for missing that deadline. You know the deadline from the first day of class. So that's March 31st. Any late submissions will not be accepted. This is something that we will have to work again throughout the entire semester because it's a very comprehensive project and we need to meet regularly to go over your progress so there are no surprises at the end. Particular time by midnight, by the end of the day. That's for submission. Then after submission, we have the presentation. You have 3 days for presentations. I booked one here that goes a bit beyond the class, the schedule. We have April 1st and April 8th during the lectures. And then I also have April 6th that it goes from 8:15 to 11. Now that is just to cover some extra time in case we need it, depending on the number of groups. I understand that there are some people taking, I think, second-year classes that may have a conflict. So if that applies to you, please let me know. All right, so keep that in mind in your calendar as well. So for the design projects, I encourage you to create groups of 4 and pick one of the projects from the list that I already posted on Canvas, or propose your own project. If you are free to propose your own project, if you're working on a personal project, a mechatronics project, and you want to use that as your design project, that would be a great idea. So long as you have 3 key components: control, actuation, and power electronics. If that applies to your project, then we should be fine. So the list that I posted is not strictly what you should work on. Those are examples of what you could do, and you can definitely just pick one of those if you're interested. But if you, again, want to do something else, if you have a grand idea to change the world, feel free to submit that, and we can work on that one instead. That's perfectly fine, but we do need to talk about it first to tailor the learning outcomes to fit the course expectations. If you miss the midterm, you need to submit a request for academic advising. It's not up to me to assess whether or not the deferred term examination can be granted. This is up to academic advising, and they inform me about their decision. So for any requests to defer or miss deadlines, consult academic advising, and then you process your request and forward it to me. If you miss the midterm, then the weight of the midterm will be transferred to the final examination. So the final examination will be 60% instead of 40%. Okay, so now let's talk a little bit about the design project. You notice that this is 20% of your grade, so the expectations are also high. So this is a significant chunk of your grades and can make a huge difference on your final grade for this class. The design project is a project they're going to work on over the duration of the course, and it must include these 3 components: the design, analysis of, and modeling of an electromechanical system. And that includes, if you're talking about a mechatronic system, a control part, a power electronics part, and an actuation part. These are the 3 main components that any of your design projects must include. We are essentially working on designing and analyzing an electromechanical system. It could be any sort of electromechanical system that involves some sort of motor and some sort of power electronics, and that is controlled by a microcontroller. We'll talk about potential projects later. The design projects will also need some sort of modeling and simulation of power circuits. And for that, you can use whatever software you like. If you're comfortable with Multisim, use Multisim. If you want to use MATLAB Simscape instead, go for Simscape. If you prefer Simulink, perfect, go with Simulink. LT-Spice, go with LT-Spice. Whatever software you like, you can use. And that includes CAD as well. If you need to design a system, a revolutionary system that you want to present to us, go ahead and use CAD. You can use SolidWorks, you can use whatever you like. Our objective here is not to work on mechanical design itself, it's more on the integration of these three key components: control, power electronics, and actuation. So form these groups of 3 and 4 students by the end of the week. Either pick a project from the list that is posted on Canvas, or let me know if you have other ideas. Can only one group do each project? No, you can pick whatever you want. You can have multiple groups working on the same project. That's fine. But let me know by the end of the week your group integrants and which project you'd like to do. And again, you can select other projects. You can come up with a project, just have to submit the idea to me, and you have a quick chat to see if that meets the expectations. So the design project will be delivered in 2 forms. One is the presentation, and another one is the report. You are not required to make any prototypes. Right? You don't need to make any prototypes, but if you want to make a prototype, you are welcome to do so, and you'll be given extra bonus on the final grade should you decide to do that. But I understand now that the current situation doesn't really allow that, but if that's still an option to you and you would like to create a prototype of your project, great. You're strongly encouraged to do that, but it's not a requirement. And if you do it, you can, I'll give you some extra bonus marks. So it has a question here. We pick and let you know the design project topic by the end of this week. Yes, you let me know your group members and which project you would like to do by the end of this week. And then starting the week after, we are going to meet. I'm going to send you calendar invites to each group, so we can go over your progress. Yes, the groups can. The maximum number of people in one group is 4. You cannot go beyond 4. Okay, any other questions here? So lab groups and projects are the same. Yeah, that would be a good idea. If you can have a lab group and a project group with the same members, that is probably a good idea. So for the design report, which is due on March 31st, these are the evaluation criteria that we're going to be looking at: technical rigor and accuracy, electromechanical modeling, electromechanical simulation, language, clarity, presentation and graphics, and project economics and feasibility. So this is due on March 31st. And these are the topics you're looking at when evaluating your design project. Notice that even if you make a prototype, if you make a lot of simulations, we are only taking a PDF that is 5 pages max, and includes all the information in your project. So you need to be very precise with your language and very precise with the information you want to convey. And this is a very good exercise to do, because this is how we present information in a professional environment. People will not take the time to go through your simulations and check them. You need to convince them that your simulations are sound and your idea works. And that's the exercise. We have 5 pages to do that. We have 5 pages to show that your idea works and how it works. And you can back that up with simulation, with CAD models, with prototypes, etc. But only I can only deliver one 5-page PDF. The last 5% is in the presentation. So this design criteria here, evaluation criteria, add up to 15%, and the other 5% is the presentation. We're going to go over the presentation soon. So for the resources we need for the project, you can use, as I said, any simulation software. I'm a big fan of MATLAB and Simscape. Simscape is an extension of MATLAB, and you can use that if you like. Oh, I have a question here. Does that 5 pages include title page citations? Yes, everything must be in 5 pages. Unless we have a exceptional project that requires more than 5 pages, you can ask me for sure if you can go beyond 5 pages, but that is the standard size. So for simulations and for CAD, you can use any software you like. I personally like these Simulink and Simscape extension of MATLAB. For drawing, I recommend you use Inkscape. It's a free software where you can sketch electrical circuits, diagrams, mechanical systems. All the diagrams that you saw in control systems, they were done by hand using Inkscape. You can also use formulas there. That's a free software. So it's not required, but it's a good tool if you'd like to use. I recommend using Inkscape for graphics. And here is a big change. Now it is time to abandon Word and Microsoft Office, right? Nobody needs Microsoft Office, other than secretaries. For Word, we have LaTeX. For Excel, we have MATLAB. So who needs Office, right? We are going to prepare your documentation using LaTeX. If you haven't heard of LaTeX, this is a software where you actually have to code your text and to code the formatting of your document. I understand that a lot of you are not used to this programming language at all. So you're going to have a tutorial that Ben will run during his office hours on Wednesday from 2 to 4. And we'll send you more information about that later. So this document preparation system is very useful if you want to create professional documents to deliver later. So we're going to walk you through that and how to use it. And it's a very good opportunity to learn how to use it. It's a very powerful tool. We don't have a graphic interface as in Word. We need to type what we want in like a code language, and then it creates a PDF that shows that. All the issues with formatting, with references, that's in the past. That belongs in Word. In LaTeX, we'll not have that. And the outcome is a lot better than Word. You can definitely look at the example I posted on Canvas. There is a module called, how is that called? Design Project. And you see the how to get started with this before there is a guide, how to get started with LaTeX, and one example of last year's project that was prepared using this software. So take a look there and install the editor. You can start working on it. But again, we are not expected to figure out how to use that on your own. Ben will give you a tutorial. There is also a template provided, and the documents that you create use this software will look a lot more professional, and you see that it's definitely worth learning. Any questions? All right, so for the design presentation, that it will be worth 5% of your grade. These are the dates that we just discussed. So 3 days at the end of the term, and there will be between 10 to 15 minutes per group, depending on how many groups we end up having. This is going to be evaluated following these 4 criteria: technical rigor and accuracy, the clarity of your presentation, graphics, and questions and answers. So we'll reserve a portion of that presentation to question your design thoroughly and see if you can defend it, if you made the right choices in your modeling, and if your design is sound. So that will account for 1%. I personally really enjoy these presentations because you see a lot of interesting ideas coming up and a lot of good work put into it. So I recommend that even if you're only presenting in one day, you come see what your colleagues did because it's all mechatronics projects and they are really fun. I really enjoy this part of the seeing that we can apply all these concepts to create like a physical with a clear outcome such as a design project. So do attend these, and you're also encouraged to ask questions if you would like to. So for this presentation, myself and the TA will be evaluating, and I will see if Masood is also available to join us and listen to your ideas. Okay. Any questions? No. All right. So I always tend to talk too much. So let's just wrap up the course overview before we go into some more details. Notes will be available on Canvas before each lecture, so download them. And as we go through them today, we are not going to use lecture notes, but I'm going to answer or go through some exercises on the lecture notes so you can take notes on your end. That is not going to be the case today, though. So do download the lecture notes and use them in class as you need. As in control systems, some of the information is missing, and the missing information will be shown during our meetings. The annotated lecture notes will also be posted later, but it's important that you make your own notes. I noticed in control systems last year that a lot of students were only studying from the annotated lecture notes, and that was a mistake. I think it was indeed actually a mistake that I made. I shouldn't have posted them, because when you look at the annotated lecture notes, everything looks simple, right? Because all the required information is there, it's given. But it's very important that you create your own lecture notes, that you decide what is important and what you need to know. Right? So make your own lecture notes, and in case you need the annotated lecture notes for extra information, then use them, right? But do not rely solely on the annotated lecture notes. That's not a good strategy. You are encouraged to attend all lectures because, as I said, these lectures will build up quickly on each other. And if there is any deficiencies, you need to fix that before the next lecture. Do not let things accumulate or you'll be lost. To give you an example from last year, let's say you didn't really understand how to do Bode plots. And then when you get to plotting a Nyquist plot, that doesn't make any sense, right? So we do need to keep up with the course contents on a regular basis and make sure that everything is clear before we move on. And if that is not the case, simply ask me that I can slow down. We can meet outside of the lecture time and go over that, right? But do not let things accumulate. If there is anything that is not clear, just let me know and we can fix that before it's too late. So the lecture notes, once again, are not self-contained. If you only look at the lecture notes, you're going to be missing a lot of information. Most of the information is delivered during the lecture, so do attend the lectures. Do your best to wake up at 8 and attend them. All right, are there any questions about the course structure, organization so far? No? All right, so these are the topics we're going to cover. We're going to start next week with magnetic circuits, a review of magnetic circuits that you saw in physics. We're going to go over them again quickly. And that will be the basis to power electronics part. So the power electronics and the electrical part of the course will be the first one. And then you're going to move on to actuators. I have a question here. We will be using lockdown browser for all examinations. Yeah. Yeah, we'll be using lockdown browser. The format will be a bit different than control systems. Last year we used it as well. We used Blackboard for the examinations. And the final exam had 50 questions, 50 short questions, multiple choice questions. And it went pretty well. So if you're required to calculate something, these calculations are very simple, and then you select or enter an answer. I must be noted that these questions that you get using a lockdown browser, as it was the case in control systems, they are built to be easier than a regular question, because in a regular question where you would be able to submit your work, typically the questions are much longer. So the questions that we have in the examinations online are a lot shorter than regular questions that you would get otherwise in a classroom. For example, last year we had 50 questions for the final exam in 3 hours. That was plenty of time. The questions are indeed short, right? And the calculations don't take a lot of steps. And it went very well. So we were saying we started magnetic circuits and power electronics. So the biggest part of the electronic component, where you have to go over electrical circuits and modeling again in more details, will be the first part of the course, the first 8 lectures. And the assumption is that students are comfortable with electrical circuits. We are going to start from where you left on electrical circuits. That will be the basis for the power electronics part, and then you're going to slowly make our way towards actuators, which is a bit more interesting in the sense that you can kind of get us more of a physical sense on how things work. We're going to start with electromagnetic energy conversion, how we go from a magnetic field to mechanical motion, and that is the basis for electric machines, electric motors. And then you're going to model them, see how they operate, how we can estimate their torque, for example, their speed, and how we can control them. And that would be the last part, is torque and speed control of electric motors. Okay, so let's look at this mechatronic control loop here. You probably recognize each of these blocks. We have, let's say you have a mechanical system that you want to control. This is our mechanical system. It could be, let's say, a robotic arm. It could be a car. It could be anything that is to be controlled in a particular specific way. To control that system, we need an actuator, which is typically the power source of the system. For example, an electrical motor, a linear actuator, or so on, something that converts electrical into mechanical energy. This is one key component in this course. Now, if you want to control this mechanical system, we need to measure how this system is behaving. And for that, we need sensors. So there are 2 sorts of sensors. The first one are analog sensors that will measure whatever you want to control and create a continuous signal. And this analog system will now have to be converted into a digital system using an analog to digital conversion, and then sent to a microprocessor. Or we can have a digital sensor. So we first convert the signals into digital signals, we measure them, and use a digital sensor to inform the microcontroller. These 2 topics here, you're taking now in sensors and instrumentation. The mechanical system that is there, we cover that in dynamics and other courses. If that turns out to be an electromechanical system, for example, then the electrical circuits theory would go in there. Actuators is the part that we're going to cover in this class. How these actuators work, how we can model them precisely. And the microprocessor here represents the controller part, where the controller is implemented. That could be like an Arduino controller, or could be a computer itself. So the microcontroller will know how the system is supposed to behave. It will take this information from this analog or digital sensors, process them, It's a digital system, so you now need to convert that digital signal back into an analog signal. So here we have a digital to analog conversion. And that is sent to that white block there. What is missing in this mechatronic control loop? Any ideas? What goes in that white box there? Input. Yes, yeah. Well, the input is not is missing from the diagram, but it would go here. Right? The expected output is in the microcontroller as well. The PID is also in the microcontroller. The controller, the transfer function, noise is also missing. Noise would be here. The error, the driver, what else we have? This is all in the microcontroller. Aha, there we go. The amplifier and the power electronics. Here we have an amplifier that is missing. We cannot power anything from a microcontroller. A microcontroller runs at a very low voltage, very low current, and therefore very low power. If you want to control a robotic arm, we are talking about hundreds of watts. Where is that power coming from? It needs to come from an external source. The power is delivered from an external source, and how much power we deliver to the actuators is the job of the power electronics component. That could be an amplifier, could be a DC converter, could be a transformer, for example, or a linear amplifier, and so on. So that is the key component that is missing in this mechatronics control loop that you haven't seen before in other courses. The amplifier and the actuator. So typically they go hand by hand because they need to be tailored based on the actuator they're going to use. If we are using, let's say, a drone motor, for example, the amplifier is a something that creates a three-phase analog output, sinusoidal output. If you're using a DC motor, then you only have one output and only one input. So really, the power electronics and the actuator, they are typically designed together, and that's why they are combined in this class, right? Everything else was covered. So I saw some questions here about the transfer function being missing. Where is the transfer function? Is the transfer function really missing? The transfer function is actually the mechanical system itself, right? We may have a transfer function in the microprocessor that emulates how the mechanical system responds to inputs. But the mechanical system is the transfer function. But we have a real system, and the real system replaces the transfer function. Now, if you want to know how the system behaves to certain inputs, then you can take a transfer function, which is a representation of that mechanical system, and then add that to the microcontroller. Where is the PID controller found? Where should that be? It's in the microprocessor. The microcontroller is in the PID controller is in the microprocessor. We are going to see how we implement that. And the error is also in the microcontroller. All right, and we'll see exactly how to implement this in Arduino. So we have our desired input, the measurement, the PID, and the error, and maybe another gain here before the digital conversion. And this entire part is in the microcontroller. It's all embedded there. Okay. We can have an external input to the microcontroller to serve as the reference point as well. Let me give you this example here. We want to control this DC or AC motor that runs at 120 volts and takes 5 amps. Will the modeling of this transfer function be much like the first half of control systems? No, no. The modeling will be a more physical, we're going to apply some physical concepts to model the actuators, and you're not going to come up with transfer functions. We're going to describe how these systems work and how we can then design them. But it will be different from the modeling we use in control systems. It's more an electromechanical design, but let me give you an example for this question. In control systems, we assume that the relation between torque and current in a DC motor was constant, was a constant gain. The question that you're going to address here is why. Why is that a gain constant? And why is there a gain between current and torque? Why is the torque in a DC motor proportional to the current? Have you ever thought about that? That comes from Lorentz force in an electromechanical system. And that's the part that we skipped before. Now we have to go into the working principle of the DC motor, model it, and then come up with the actual relation that will show us that the torque depends on the current in the same way that the back EMF force generated in the motor depends on its speed. Right? So that modeling that it was assumed before just to be a constant will be the focus of an entire lecture. How do we get that constant? How do we model the whole system? It's quite interesting. So back to my example here, we have this 120 volts, 5 amp motor, and you want to control that using a microprocessor. The microprocessor, if you're talking about an Arduino, runs at 3.3 volts and may deliver up to 50 milliamps. You're not even close to the power we need. What do we put in that amplifier? Can we use an operational amplifier? Yes, we can use an operational amplifier, which is basically simply a linear gain. We are increasing the power linearly, but that's a major limitation of linear amplifier is that they dissipate a lot of energy and therefore they are not very efficient. So operational amplifiers are not part of power electronics. Transformers. Could you use a transformer instead in this example? Likely not, because a transformer only works in a with AC signals. It doesn't work with continuous current. So this also doesn't work. The way you are going to be able to control this motor is to use a digital, a DC to DC converter or pulse width modulation. The idea is very simple. It's not very elegant though. We take the power source and we have the motor here. And here we let's assume we have a switch. If the switch is on, the power is delivered to the motor. If the switch is off, the power is not delivered to the motor. This switching may be controlled using, for example, a transistor, a MOSFET, or something. Depending on the, now we can take this microprocessor and use it to open and close that gate. But that happens at a very high frequency, let's say 50 kilohertz. Depending on the timing for which the gate is open or closed, that dictates how much average power is delivered to the motor. You see, this is not very elegant, but it's how it is implemented. So we are going to keep opening and closing that gate there. And depending again on the time, let's say we have a frequency of, we're doing that every second. It will happen every maybe 5 microseconds, but let's assume for simplicity that it's every 1 second you're going to switch that. Within that 1 second, we can choose to have the gate halfway open half of the time and close for half of the time. This way, half of the power is delivered to the motor. Or we can choose to do, let's say, 10% on and 90% off. Then 10% of the power is delivered to the motor. And that is controlled in the microprocessor. What if we need now to reverse the power? This power flows in one way. What do you have to reverse the power? Then you need another one of these that is reversed. And the question here that Mark is asking, is this like the duty cycle? Exactly. This is exactly what it is. It's a duty cycling. It's a pulse width modulation that you're going to use to emulate this average power delivered to the system. And notice how interesting this is, because the microcontroller's job is not to deliver power, it's just to open and close that gate. The power comes from an external source, right? Completely external to the microcontroller. The microcontroller and the power unit are separate. This is a very, very simplified example, but for, let's say we now want to use a DC signal to create a sinusoidal signal, because a lot of motors are AC. Let's think about a drone, for example. If you look at a motor, the motor that is using in a drone, this wouldn't work because this only provides DC power, DC average power at the output. A drone would require a sinusoidal waveform. So now how do we time this gate to create a perfectly sinusoidal waveform in the output from a DC input? Isn't that interesting? And it's doable. And that would be the job of a DC to AC converter, or an inverter they're going to address in one of the lectures. So this is what power electronics is how to interface a low power system with a high power system, and being able to now move from AC to DC, from DC back to AC, or even between different levels of DC voltages. If an example, a very simple example, is to look at your phone. You have one battery. That battery has a fixed voltage, and that voltage is DC. But there is a lot of components in your phone that will work on DC, but at a different level, either higher or lower. We cannot use a transformer because a transformer does not work in DC. So how is that converted? How is the voltage converted between different levels in DC without using a transformer? Well, the idea is pulse-width modulation, duty cycle, and so on. So we're going to go over all that first before we model how the motors actually work. Here is an example of a power unit. Does anybody recognize this? This beautiful arrangement here? Aha, that's an H-bridge indeed. Right, that's an H-bridge. See each of these transistors here, each of them work exactly like that gate that I mentioned. But now we have 4. Now notice that if we let this one and this one close, then power flows this way. If we do these 2, then power flows that way. Right? And you see that there is a motor in the center here. So the motor would be running in the opposite direction. And if you do this one and this one, then you burn down the house. But the idea is that now we can control the way the power flows in there. So this is a H-bridge as an amplifier that most people who did any project with an Arduino and a motor used without maybe knowing what it was. But that's the arrangement that we have for an H-bridge. So this works to convert a DC voltage into either DC voltage with a different level or even a AC voltage if we are able to time how fast and how precisely open and close these gates. Okay, we are going to go over this one specifically in detail. It's quite interesting and quite useful. So the motor drive, you'll be given one of these for the labs, and you'll also be given an Arduino and a motor, at least one motor, I think a DC motor and likely a stepper motor and a servo. I'm going to go over them in detail. Let me give you another example here. We have, let's say, a common application of power electronics and very prominent these days is the use of electric cars. You notice that in an electric car, we have a battery. The battery runs in DC. Okay? So we can simply charge the battery from our grid, but let's assume, for example, that we have a hybrid car, or in the case of locomotives. Locomotives actually run with electrical motors, but they have an engine generation system. You have a big engine. The engine runs, is attached to a generator. The generator creates AC power, and that AC power is used to run the motors. Because there's so much power involved in a locomotive that transmission, doing that mechanically would be very complicated and would fail easily. So it's actually converted, the mechanical energy from the motor is converted into mechanical energy before it is converted back into into mechanical energy through a motor. So this is the same for hybrid cars. Let's assume you have an engine that turns a generator. The generator creates AC power, right? A alternative current. We cannot put a battery on AC. If you put a battery on AC, the battery will charge and discharge at every cycle, right? So that doesn't really work. So before we attempt to charge the battery, we need to convert this AC into DC and then charge the battery. So power only flows one way. And that's the first step. Now we take this AC voltage, we need to convert that in DC, and that's basically all these converters that we use at home to charge a phone, for example, of course, at a larger scale. Now we have a battery and we have a DC power. How do you now go from a battery to a electrical motor? Most of the motors that are high power and will, for example, be used in cars, they are AC. They are not DC motors. They run with probably three-phase AC. Now we have another problem, is that our power is stored in a DC fashion. What do we do? Now we need to convert this DC power back into AC to be able to power the motor. And that's done through this inverter. It's the same idea that we discussed before with that gating cycles with, say, a scaled H-bridge, and a controller that now determines how much power the motor must be taken to control the speed, the torque, and so on. Right? So you see how interesting this loop is. We go from AC to DC, from DC back to AC to be able to control the motor in an electric car or in a big locomotive. And then the controller is what determines how much power is delivered to the system. Right? So here is one component of power electronic system, is the AC to DC converter. Here is another one, is the inverter that now goes from DC back to AC. And the controller that will maybe measure, let's say, the power at the motor shaft and then adjust the duty cycle, the pulse width modulation, and the gating sequences that we need in order to create this AC signal. Okay. Here is another example of, this is the most elementary mechanical electrical machine that we could think of. It's very simple. You can build this at home. It's easy to make. So all you need here is to have a ferromagnetic material. These two pieces are ferromagnetic. We create a coil around one part and you turn that on. Basically, we turn this into a magnet. This is an electromagnet, or what we also call a Lorentz actuator. If we apply a current through this coil, then there will be a magnetic flux established in this circuit. And this magnetic flux now turned this system into an electromagnet, and now a force will be applied between these two parts. And the core and the other part will now move together. Right? And when you turn off the voltage, then the spring pulls that plunger back. So now, depending on the intensity of the voltage that you apply, or the current, which determines the magnetic field, you can determine how much displacement you can achieve. And this is exactly how a linear actuator works, how a solenoid works. Right? There's a lot of questions that we could ask ourselves here. How does the current relate to the magnetic field? How does the magnetic field relate to the force that is being developed there? What is the influence of the material in the performance of the system? How can you power, model, and control this actuator? That's the whole idea. If you want to control this actuator, we need to understand how it works. And we also need to develop the necessary power electronics unit for that to work properly, right? And this is how a solenoid works, and is the most elementary electrical machine that we can make, and it's easy to do at home. What is this? Has anybody seen this before? Does this ring a bell? These are stepper motors based on the same principle. But now instead of having a linear motion, we have a rotary motion. And we can put a magnet inside there, that a configuration. And now again, depending on the voltage that we applied, or now also on the sign of the voltage that we apply to the system, the magnet inside will rotate clockwise or counterclockwise. It will tend to align itself with the stator. We can now create more of these elementary building blocks here. So we take one of these, let's say this one, we replicate that, we put more of them in around a core, and that gives a motor. That's basically how a stepper motor works. So we're going to go over that in detail as well, to be able to model how a stepper motor works and get a better grasp on the physics behind it. So these are the types of motors that we're going to study. So as I said, the first part of the course is the power electronics. I think what I heard from folks who took this class before is that it was a good idea to keep that on the beginning because it's a little more complicated than the second part. All right, so it's good to be aware of that. It's not extremely complicated. There's not really nothing new in terms of electrical circuits. It's more an application of electrical circuits to specific arrangements that constitute these drivers that we need. But it is a bit more complicated than the second part. And then in the second part of the course, which is the actuators part, we're going to go over these types of motors. We will classify them into two main categories, AC and DC. And AC motors, you're going to go over asynchronous, where we have a rotating magnetic field and something inside of the magnetic field that is magnetized and runs at a lower speed. We have synchronous motors, where now the inside core has its own magnet and now runs at the same speed as the magnetic field, and variations of those. We're going to look at a DC motors as well, stepper motors, how they work, how we model them, reluctance, permanent magnet, and hybrid versions, brushless DC motors, such as those that you can use for drones, linear solenoids, and special machines, special arrangements that we could also consider. So I have some applications here, but I'm not going to go over all of them. There are many applications of what we're going to use here. And I think you already guessed, this is an essential part of any mechatronic system design. When you do a mechatronic system design, we always have a power electronics and an actuator and a control component working together. And this could be used for force control, for speed control, for velocity control. For example, if you remember this inverted pendulum from lecture 1 in control systems, we could, for example, build a control system where either the speed of the pendulum bob is 0, doesn't change, or the position doesn't change, it's always vertical. To do that, now we need to add the extra layer to our design. Before, we were concerned with transfer functions, and okay, our transfer functions are a very good representation of the system, they are perfect. Now we need to also look at the power electronics component, because that changes the transfer function of the system. That plays an important role. We need to add that to our design, we need to take that into consideration. We can also see velocity control of motors in drones. If you have a AC motor, which is the case in a drone, how do you control the speed of that motor? Right? It's not sufficient anymore to just assume that the speed is proportional to voltage, because it's not how, well, it is sort of how it works, but it's more complicated than that. And you need to look at that to understand exactly what is going on. So this is to give you an idea about the sort of design projects that we can consider for this course. I have a few here from last year. For example, the first one is a transducer for kinetic energy harvesting using a full wave ratification. So the students who work on this project, they had a float on the ocean that would move up and down. They connected that to a magnet and they had coils around it, and then they managed to estimate how much power that would create. An actuation system with analog PID grasping force controller of a hand prosthetics. So for a prosthetic hand, you want to control position or force. You need to fully understand how everything is connected from the mechanical part through the power electronics, through the actuator to the microcontroller. And this is also a very interesting project that we saw. Linear induction motor of electromagnetic levitation and propulsion of a train. You probably heard of maglev. Is magnetic levitation train, was created in Germany. There's, I think, one in China that actually operates, the only one that operates. How is that possible? How can we actually make a train levitate and propulse it at the same time? This was one of the, and actually power that. How much power would that take? So it was a project, and this is the one that is posted on Canvas from last year, one of the best reports that we had last year. And the list goes on. So these are suggested projects, just to give you an idea of what it can be done. More than suggested, I would say recommended projects, because they cover all these three parts. But you can also propose your own. Again, if I want you to be working on something that you are interested in and you can spend time working on, not something that you just have to do for the sake of doing it because it's part of the class. I want you to be working on something that you see yourselves working on and that you are interested, genuinely interested in. So if none of these projects are interesting enough, then you can definitely propose your own project with your group. Especially if you have your own personal project going on, we can turn that into your design project and you can work on that. Once again, you are not required to build a prototype. Everything can be done in simulations, in CAD, and so on. But should you decide to make a prototype, you will be given extra bonuses for that. And you've seen very interesting prototypes last year. Another thing that is very important to keep in mind, and this is extremely important, is that we meet with me or Ben during the term at least every 3 weeks, 2 to 3 weeks, to go over your progress. This is really important. We don't want to leave this for the last minute because there's a lot of work. It's something that you have to work on through the entire term. And if you have any questions, we are here to help you with that. So do not let things accumulate. Once I have a list of all groups, I will send you some calendar invites to meet and go over your progress, not just to push you to work, but also to guide you through the process of creating these systems, right? That takes a lot of extra time from myself and from the TAs, but we are doing that because we genuinely want you to be working on something that you like, and we want to see that done well, something that you can show later that you did and that you're proud of. Right. Let me show you one example from last year. So this is a dual solenoid engine that was proposed last year. You see, if you see my mouse here, these two elements next to this rotary system are two solenoids, the Lorentz actuator that we talked about before. And these guys put two of them together to create a solenoid engine. So the key question here is how to time these two guys and model them to now convert this electrical motion, the electrical signals, into mechanical motion and then into rotary motion. And you see the Arduino behind there that was done in Arduino. Isn't this quite interesting? It's an interesting motor with two solenoids, but you can use more if you like. This is one possible project that you could work on. Right? And the prototype is here, but the focus, once again, was not prototyping, was the simulation and control of that, right? Say we want it to run at a very specific speed. What is the timing of the solenoids that is required to do that? Okay. There are examples posted on Canvas, and that is a summary of what we discussed today. So these are the main parts of your project that will have to be included if you decide to propose your own project, or even, of course, if you work on those that are already proposed there. We have a controller, power electronics, and the actuator. Those elements must be in any project, and this will be the focus of our course. For the mechanical system, if you like to, say, build a robot, you can take open source CAD models from any source and you can use it, because our objective is not to design mechanical systems, is to integrate a mechanical system with a microcontroller through the power electronics and an actuation unit. Okay, so this is very useful for any mechatronics project. These are the review topics that I would recommend you review if you like. Fundamentals of electrical circuits, but I think you should. Mechatronics students typically don't have any issues with that. The notion of effective power, RMS voltage, peak voltage, etc. Electromagnetism, feedback control, we just took that, that's fresh. Electromechanics, we're going to use Arduino and C++ in the labs. And transistors, diodes, and operation amplifiers. We are going to cover all these topics, but if you have seen them before and you want to refresh your memory, these are good topics to review. Next week, we are going to look at magnetic circuits. This will be the first lecture on magnetic circuits. And from there on, we are going to go from magnetic circuits to transformers, to rectifiers, to DC converters, to AC converters, and slowly make our way with towards actuators, starting with elementary machines, and then adding more and more up to the point where you can fully understand how a big three-phase AC machine works and how and what it takes to be controlled, what is the power electronics needed for that, and how that can be precisely controlled in terms of torque or speed. Okay, so that's it for today, folks. If you have any questions, I will be available. I will post some lecture sometime later today on YouTube. I will keep this one private, not available to everyone. So if you have any questions, don't be afraid to ask questions, because the videos are recorded. I can just edit that. So they have a few more questions here. Can you expect to get a full scope of what each section of the design project needs as we progress through the course? Yes, that's why we need to meet together. We need to meet and go over what you're doing and see what we can add, right? So the expectations and what should be included is really dependent on the project you choose. That's why we need to meet and go over that. Would you be able to post a list of all the students' labs CRNs to make forming a group easier? That's already available on Canvas, and you can form groups with people from a different lab section. That's fine. You can take anyone you want. The LaTeX section on Wednesday will be recorded if I can make it. Yes, same style, but I strongly recommend that you try it so you can ask Ben questions on the LaTeX tutorial, and he can help with you can share your screen, you can go over the questions with him. Right? There is also a lot of documentation on LaTeX. That's true, and the documentation, some of it is already posted under Design Projects tab on Canvas. But again, you're not expected to figure out how to use LaTeX yourselves. We're going to help you with that. Any other questions? No? All right, so that's it for today. I'll see you again on Thursday. I will have office hours now. If you have any questions, I will just need to end this meeting. I will start it again. So if you want to attend office hours, just log in again in a few minutes. All right. Thank you, everybody. Have a good day.